Hey everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting a new chapter basically, that is the Nyquist plot. It is obviously coming into the frequency response topic only, but here right we'll do a bit of different analysis and we'll understand why do we need Nyquist plot and what are the principles that are used in this plot, right? Many people they just mug you up the formula about the number of encirclements n equals to p minus z, right? So but obviously we have to know that that formula is important, but how did that formula came up, right? And what are the concepts behind that formula, also we'll learn about that, right? So what we'll learn in the lecture 1 of Nyquist plot. So in the next lecture 1 of Nyquist plot, basically we'll learn about the mapping theorem. What does mapping mean, we'll understand, then we'll use the mapping theorem, and then if we have enough time left we'll understand also the principle of argument. But before that we'll do few examples on mapping, right? So what is the concept of mapping? Let's read the definition. The relation between points in two planes is known as mapping or transformation. What does this mean? So you since childhood only we study, right, functions. So I can write x f of x as a function of x, right? Okay, like y as a function of x, y equals to f of x, we write, right, which is a function of x. What does that do? Which is a function of x. So we are mapping our variable x into y. Let's say y equals to x square. So for y x equals to 1, what does y become? Y becomes 1. For x equals to 2, what does y become? Y becomes 4. So for every unique values of x, we are getting unique values of y. So we are basically mapping this x, right, to y. Okay, mapping this x to y. Okay, we're just changing the variables. So that is what mapping is. Now why is it used in Nyquist plot or in control system, that's it, right? So each and every point in S plane will be mapped to corresponding imaginary of g of h of s versus real of g of h of s plane, right, where g of h of s is a function of s. Okay, obviously you will not be able to understand, but each point on my S plane, right, each point on my S plane, like the poles and zeros, whatever it is, you will not be able to understand this. Just read this point, right, that will be mapped into that polar plot graph, right? Polar plot like graph. X and y axis are same, real and imaginary. Okay, so why is this important? Like again, right, what is our main target with the frequency response? What is our main target? Main target is to find the stability basically. So this, right, if we map this one, this will help us find the stability of the system. This will help us find the stability of the system, right? So yeah, that is our main aim basically, to find the stability, right? So we will obviously get more in depth to this, but obviously I'm just giving you the definitions, right? What does mapping is and why we use Nyquist, right? So one more thing, like why is mapping important here? But we are finding stability through that what do you say, like the polar plot also, but that was relative stability, that was not absolute stability. Here, right, we will be able to find absolute stability, right? But why is mapping important? Why are we using mapping? So what defines stability basically for a system? What defines stability? For my system to be stable, right, for my system to be stable, I have to check even if there is one pole lying on the right hand side of my S plane of my closed loop transformation, right, CLTF. If I can check that, right, if I can find that there is at least one pole on the right hand side of my S plane, then for sure 100% my system will be unstable. That is correct, right? So that is what we did in Routh Hurwitz criterion, right? We found out how many number of poles are on the right hand side of my S plane. So here also we'll do the same. We have to check how many poles are on the right hand side of the S plane. But what is the problem? The problem is I have to check till infinity. So like my graph will start from here, right? Graph will start from here to infinity. Okay, on the right hand side, this is sigma j omega plane. Okay, so I have to check for all these points if they exist on my CLTF. Like I will put all these points, put it in the CLTF equation, right, characteristic equation, and check if any of these points are valid roots of those characteristic equation. But that is a hectic task, right? That is a very hectic task, right, to check the infinite amount of points. So what we'll do, we'll map this infinite amount of points to a function and then check for that function if it is satisfying that condition or not. So you will not be able to understand what I'm saying, right? But if any of you are able to understand, that is good. That is good, right? You got the concept of mapping. So we are mapping this 0 to infinity points, right, into some finite amount of points through which we can check whether any of those are satisfying the equation or not. Okay, like this is the manual thing that I'm talking about. Obviously we'll not actually check manually this will be automatically done with the frequency response, right, with a plot. But this is a basic concept why mapping is important. Okay, so basically what is the first thing? For CLTF to be stable, no poles should lie on the right hand side of S-plane. Okay, no poles should lie on the right hand side of S-plane, but it is very difficult for us to check for all the infinite amount of points. So we have to check for the whole right hand side of S-plane. Which is hectic, right? Which is hectic. Hence what we do, we simply map those points. Hence we simply map those points, right? And it becomes easier for us to analyze. To make it easier for us to analyze. Easier for us to Okay, so now let's basically map between a rectangular plane and a polar plane. So I hope you know, right, what a rectangular plane is and a polar plane. So rectangular plane is something like this, like it is defined by 2 points x and y, right? X is here in the x-axis basically, and y is in the y-axis. We have been studying since childhood this one, right? And what is a polar plane? So polar plane, right, it is defined like the distance from the origin, okay, and the angle from the positive x-axis. So polar plane, like this z, right, we can write it in polar plane also. How? Basically this would be r e raised to power j theta, right? Okay, and what is r? R equals to under root x square plus y square, right? R equals to under root x square plus y square. And what does this mean? This means the distance from the origin. Origin is where? Origin is at this point, right? Okay, when where the two axes cross each other. So this is known as the distance from origin, right? Okay, so I will write this in next page. Basically we don't have enough space here. Okay, and what is theta? Theta is basically the angle from the positive x-axis, right? And what is the formula for it? It is tan inverse y upon x. So theta equals to tan inverse y upon x, which means that it is the angle from the positive x-axis, right? Positive x-axis. Okay, so this is about like the x and y coordinate. Now like let's say if I want to map these two planes are same only, right? But like they are, let's say they are speaking different languages but they mean the same. Okay, like आप हिंदी बोल रहे हो और I'm talking Hindi. Okay, both of them mean the same thing, but one is speaking in Hindi language and other one is speaking in English language. So what do I mean by this here, right? So if I point, let's say I take a point x and y 2,1. So I take a point in this plane as x equals 2 and y equals to 1. So I go 2 steps along the x-axis and 1 step along the y-axis. So this is 2 comma 1, right? This is 2 comma 1. Okay, so this is 2 comma 1. Now what if I want to represent the same point here? This will be same only because the planes haven't changed. It is again real of z and imaginary of. What does real of z mean? Simply x, right? And what does imaginary of z mean? It means y. Here also we are just like representing it in terms of distance. So this point, right, still will be in here, but now I will represent it in a different manner. So what will be my r this time? The distance from the origin. So my r, right, this time r will be, okay, when my x and y are 2 comma 1, simply equals to 2 square plus 1 square under root, which is simply equals to under root 5. So r is under root 5, and what is my angle? My angle is basically tan inverse. Which is equals to 26 point, like it is known, right? This is like simply 26.56. I think tan inverse 2 you have to like remember 26.56 degrees, right? So this is about my angle. So this will be, or you can write in radians also. So in the positive x-axis basically. So you will see, observe that the location of the points are same, right? Just the way I represent those have changed. So this is like, this is not like a like complete mapping, right? What does mapping means? Mapping means we want to map like into a different plane itself, right? We want to map in a different plane itself. So how will you map? Basically we'll take a function, new function itself. So let's take a function which is a function of this z, right? Let's take a function f of z, okay, which is, let's say, like any function we can take, right, which is z square, right? If my f of z equals to z square, now where does my previous point lie in the new axis? Okay, new plane basically. So now I am mapping, right? I'm mapping into a new plane. So this z is 2 plus I. So this is 2 plus I whole square. So this becomes like I know a plus b whole square, right? So 2 square plus I square, 2 into I into this 2, right? So this becomes 4 minus 1, so 3 plus 4i, right? So this was 3 plus 4i. So that previous point, what was previous point? It was 2 comma 1, 2 comma I, right? Now it become 3 comma 4i, okay? 3 comma 4i. Now it is mapped, right? So what will my new axis look like? So I will take this previous point, right? Previous point here. So if I map this one, right? If I map this one, okay, to the new plane, now what is the real part of f of z, not the z, right? So this is a new plane. That is what mapping is. We are just mapping into a new plane basically. So z okay. So yeah, now like where does this one lie? This lies like like 3 steps from the positive x, like this is not x anymore, this is a real of f of z axis. So real of f of z axis, 3 steps here and 4 steps on the positive direction of imaginary of f of z axis. So 3 steps here and 4 steps here, so somewhere around here, right? Okay, as you can see, this is 4,1 and this is what mapping is. So my point, right, my point is simply mapped. So this point has been simply mapped here, right? So this is what my real and imaginary parts are. So now let's take one example, right? So let's take an example, right? Let's take an example that I have f of s, which is equals to s plus 1 divided by s plus 3 basically, right? S plus 1 divided by s plus 3, and this is basically, what is s? S is the sigma j omega plane, right? S is the sigma j omega plane. Sigma j omega plane, right? So s is the sigma j omega plane. Okay, so what I will do, I will just vary all the points of s and I will find the values of f of s for that. And what I will do, I will plot the real of f of s and the imaginary f of s. Okay, that is what I will do. That is what basically what in Nyquist plot we do, right? Nyquist plot we map, but we are not able to see it because that is hidden. When we will solve question, there you will understand. So what we will do is, take all the points of s and put in f of s, right? Take all the points of s and put it in f of s, right? So yeah, like basically we will vary s and put it in f of s. Now what else we'll do, we will plot basically imaginary of f of s versus real of f of s, right? We'll plot this one. Okay, and that will be basically our Nyquist plot. Okay, so like how will you vary? So what you can do is you can separate out the real and imaginary parts. Okay, so how will you vary? Like what you will do is you can write your f of s equals to s equals to what? Sigma plus j omega. So I will replace s here with sigma plus j omega. So it will be sigma okay. So this is basically sigma plus j omega. Now what does this become? So what I can do, I can simply use rationalization, right? Simply use rationalization to separate this real and imaginary parts. So this is sigma plus 1 plus j omega and like after rationalization, right, what will this become? This will be sigma plus 3 whole square plus omega square basically. Now you can simply separate the real and imaginary parts. So this is oh, I cannot even write the sigma plus 1, sorry. This is sigma plus 1 into sigma plus 3, and this one is also, this becomes plus omega square, right? So this multiplied with this and this multiplied with this also yields as a real part, a real component. Okay, yeah, this is plus basically. So now this is this one. And what is the imaginary component? So the denominator has itself that sigma plus 3 whole square, right? Like plus j omega sigma plus 3 minus sigma minus 1, right? Okay. Okay, so yeah, this is what like the real and imaginary components are. So basically, right, I can separate the real and imaginary components. Let me write it down a bit better. So did I do something wrong here? Yeah, I did minus j, yeah, fine, minus j. So let me write this one. This becomes basically this is same only, right? This is same only. So I can simply copy this one. And the imagining part just changes a bit. So it is plus j, sigma gets cancelled, right? We're left with 2 omega plus omega square, right? So this is what my f of s is. Let me take this to the next page basically. This is my real of f of s. This is my imaginary of f of s, right? Okay, so real and imaginary. So simply just vary sigma and omega, and our real part and imaginary part will vary, and we'll just plot our graph. Okay, so this is how we basically map the things, right? Map the things. Now let's start with contour. So what is a contour basically? So contour, let's read the definition, right? So the shape of the outer surface of a curve is known as the contour of that surface. So this is the shape, right? This is a shape basically, and this is a surface basically. So what is a surface? Surface is covered by lines, right? So surface area, you can say, like you can touch something, right? You're touching the surface, right? So what is the surface? Surface is this one, whichever is inside this contour. Okay, they are interchangeable. So what is contour? Contour is the outer surface of a curve basically. This is the curve, right? This is the curve, let's say this is like also a curve, right? So outer surface of this one is the contour, like just the outer part of them, right? That is known as the contour. Okay, and obviously this is known as the inside part of the surface, right? So yeah, this is what a contour is. So yeah, I hope you have heard about contour or something somewhere else. So you have to understand what does a contour mean, right? Contour is this curve, right? Outer surface. That is enough for your definition. So now let's start with example problems, right? So what is this problem telling us? So we have to map the following contour in f of s plane, right? In f of s plane, if f of s equals to s plus 1, s plus 3, s plus 1 s, and f of s is equals to s by s plus 2. So there here, right, what I told you, that we are varying whole sigma and omega, right? We're varying everything from minus infinity to infinity. Sigma and omega can vary from minus infinity to infinity. Omega will also vary from minus infinity to infinity. Why? Because we are using the mapping theorem, and mapping theorem takes all the real values, right? That's why, like, we are not thinking about omega here as a frequency or a I mean a practical term, right? Okay, so what I can say, sigma infinity to infinity. Sigma varies from minus infinity to infinity, right? And also sigma and omega, right? Sigma and omega, so they are here, right? They are just simple mathematical parameters for using the mapping theorem. So these are simple mathematical parameters, right? These are simply mathematical parameters. Okay, now, right, now if these are simple mathematical parameters, I'm not thinking omega as frequency, so I will write here, we are not thinking omega as frequency only, hence it will go from minus infinity to infinity, right? Omega will vary from minus infinity to infinity. Okay, this is one important fact to note here. It's in Nyquist plot, right? And it will vary from minus infinity to infinity, and obviously it will be symmetrical about the real axis. While solving the questions just now, we'll understand. Okay, but like mathematically also you can understand that this will be symmetrical about the real axis. We'll understand, right? So basically we have to, like, this is my contour. Okay, we have to map the following contour in this f of s plane. What does this mean? Basically I am varying my points sigma and omega here, right? So whatever variation I'm making, how is it mapping in this function? What are the values? Let's say for s equals to 1, what are the values of this ffs, and then I plot the ffs. So let's just do one example, and from there we'll understand. So what I will do is I will take 4 points that which are easy to solve. So I will, like, in this contour I will take 4 points. Obviously you just can't do it, like you can't take each point and just plot it, right? That will be very very difficult. Okay, I have made one Python function, right? And in Python function I will show you the exact plot what this will come if we map this to f of s, right? But manually it will be very time consuming, but we can get a brief idea. And after this lecture, right, or like in few slides, we'll understand how to totally get a brief idea and good idea of how this mapped contour will look like, right, when some contour is given. Okay, there are few rules which I will explain to you, and there we'll understand. So let's first take this first function, basically f of s, right? Let's take this first function. So this is basically my first function, right? And this is my contour. So what I will do, I will take 4 points, right, critical points. I will take 1 comma 0, I will take 0 comma minus j. Like, okay, I'm going this anti-clockwise direction, so I will take those type of points only. So 1 comma 0, 1 comma j, minus 1 comma 0, and 0 comma, sorry, this is minus 1 comma minus j. Sorry, this is actually not 1 comma j, sorry, this is 0 comma j, right? Like x distance is 0 itself, sorry. So yeah, this is 0, this is also 0, right? So yeah, now let's start with s equals to 1. So what does my f of s become, right, when my s is equals to 1? So my f of s, right, when my s is 1, equals to simply 2 by 4, right, which is equals to 1 by 2. So f of s is 0.5. So this is what mapping is for some particular value of s, like s is mapped into this f of s. We'll obviously plot that, and there you'll understand better. Now this one was the first one. Now let's do the second one, right? Let's do the second one. Okay, let me just check whether everything is recording or not. Yes, this is recording, this is recording. Yeah, fine. I just sometimes get tense. Okay, what is the second? So s is minus j, basically. When my s is minus j, what does this become? So when my s becomes minus j, sorry, not minus j, sorry, plus j, right? When my s becomes plus j, then my f of s, right, f of s at s equals to minus j equals to minus j plus 1 minus j plus 3 equals to, now what do we have to do? We have to do simple rationalization, right? So if I do simple rationalization, this one becomes 9 plus 1, and we do this like this one, that this becomes, sorry again I'm doing some mistake. This is plus j. Okay, I didn't have sleep yesterday, that's why just my brain is not working. So like we will rationalize, and like we'll multiply by what? We'll multiply by 3 minus j, right, in both numerator and denominator. So if you multiply that, so j plus 1 into 3 minus j is this one. Now this becomes 3j plus 3, right, and this is plus 1, and this is again minus j, right, minus j divided by 10, right. So if I go to the next page, okay, this one has cut down a bit, this real of s part, okay. So like this one becomes like let me just make this a bit smaller, right. So this becomes basically 0.4 and minus 0.2 j, okay. So yeah, this becomes 0.4 and 0.2 j, okay. So no, sorry, not minus, this is plus. So direction is what? In the first quadrant. So like my contour is rotating in the anti-clockwise direction, this is also rotating in the anti-clockwise. What is the significance of this? We'll understand later, right. So just like you solve it for yourself, right. Now you do the other 2 points by yourself and just check my answer, right. So now putting s equals to 1, this is the third case, s equals to minus 1 basically. So if I put s equals to minus 1, what is happening? If I put s equals to minus 1, my this mapped function in, right, it is going to 0. So if my contour touches the 0, okay, like the 0 of my mapped function, then what happens? It will always, like the mapped function will always go to the 0, obviously that is understood, right. If it, like here is a 0 and there is, like the mapped function has a 0 here and my contour is going through that 0, obviously it will like map function will be 0 at that point, right, at that point, okay. And what about the pole? If like my contour is touching a pole, right, what will happen to the map function? It will be infinity, right. That is the definition of my pole, and definition of my 0 is basically at that point it will be 0. So simple definitions we are using, right. So or you should simply put s equals to minus 1 and you will simply get 0, right. Contour is touching my touching 0 of mapped function f of s, right. Contour is simply touching map function f of s. So yeah, like then obviously my f of s will be at s equals to minus 1, it will be simply 0, right. Okay, so again, right, what is like the fourth point is 0 comma minus j. So again, like at s equals to minus j, what does it become? So like my f of s at s equals to minus j, simply it becomes like it is s plus 1, right? So it is minus j plus 1, and it is minus j plus 3. So basically it will be 10, right? 10, and this will be simply 1 minus j into 3 plus j again, right? Okay, so this is simply 3 3, and then this is plus 1. Okay, minus j into plus j is minus j square, and j square is minus 1, so it becomes plus 1, and this is simply minus into 3, and this is 1 times j, so this is minus 2j divided by 10 basically. So this becomes 0.4 minus 0.2j. Now do you notice anything here? So previously, right, we had, like, at s equals to j we had point plus 0.2j, and s equals to minus j we are having minus 0.2j, right? So what is happening? The real part is still same, 0.4, positive 0.4, right? Just the imaginary part is changing. So obviously what is happening about the real axis, right? Real part is same, okay, but it is symmetrical about the real axis. Okay, it is symmetrical about the real axis. So obviously, as I told you already, right, if you vary like this s, right, our this map function will always be symmetrical about my real axis. We'll see with few more examples, we'll see. Okay, so like I put it in a Python function, right? I made a Python function by myself, and wasn't able to make the axes, but here I can make it manually. So this is my real of f of s, right? This axis is my real of f of x. Okay, and what is my imaginary? Imaginary is here itself, right? Imaginary is here itself. So imaginary is this one, right? So it is touching 0 at s equals to minus 1 basically, where I have a 0 of the map function, right? Okay, so this is imaginary of f of s basically. Okay, this is imaginary of f of s, right? So this is basically imaginary of f of s, right? So now, like, from here you can understand that we're starting from this point, right? We're starting from this point, which is like at s equals to 1. At s equals to 1, what is our value? S equals to 1, we're starting with 0.5. So this is 0.5, right? Real component is 0.5 and my imaginary component is 0. Then we are going in this direction. Why? Because as I told, right, this is plus 0.2j. So obviously I'll move in the first quadrant, right? First quadrant, like something positive. So I'm moving in this direction and I'm reaching here, right? Not here. So here, right? Here, like, my real component is 0.4 and my imaginary component is 0.2. Okay, and it is touching, like, crossing this both 2 points. So like while coming back, I'm again coming to this point. So it is symmetrical, right, about the real axis. And here, right, obviously I have a 0, so it becomes 0. So yeah, this is the plot for this one. Now what I will do is, like, I will pause the video, I will solve the other two functions, right? Solve the other two functions, but you solve it for yourself. This is not like any rocket science, so you can solve it very easy, right? Just you have to put the points and draw the contour and just the behavior. You don't have to exactly draw the contour like this, right? You don't have to, just have to understand the behavior. Is it going, like, after the first point you put, right, is it going in the anti-clockwise direction or in the clockwise direction? That you understand, that is good enough. Or is it crossing the origin or not, right? Here it is just touching the origin. So here, right, it is touching the origin. Here it is touching the origin basically. Okay, so yeah, I will just pause the video and you do all the other two functions by yourself. Okay, so I hope you have solved the like equations, right? So I have done it like in behind camera basically. So here, right, if you put s equals to 1, simply you will get 2 by 1, and if you put s equals to j, you will get simply this is j plus 1 by j. So if j goes in the numerator, right, then this becomes 1 and this goes to minus j, so 1 minus j. Okay, if s is equals to j. Now again, if s is equals to minus 1, what do you notice? Again you get 0. Why? Because my contour is touching the 0 of my mapped function, right? Mapped function, my contour is touching the 0 of my map function. So if I just put s equals to minus 1 over here, obviously I will get 0, right? That is the definition of a 0. So yeah, now if I put s equals to minus j, what do I get? S equals to minus j, simply you put and you will see you get 1 plus j. You get 1 minus j over here and 1 plus j. Again, right, you are getting what? You're getting symmetrical about the real axis. Real part is same, but the imaginary part is just the conjugate of that one, right? And what is the other thing that you need to notice? Other thing that you need to notice is basically I'm putting plus j, so I'm going in the anti-clockwise direction, right? Anti-clockwise direction, and the map function is going in the clockwise direction, right? So something has happened now, right? What has changed? We have to notice this. Obviously we'll get it in the conclusion. I write this in the conclusion that if I'm moving in the clockwise direction, I'm going in the anti-clockwise direction, right? So basically this is moving in the map function is moving in the clockwise direction. So mapped contour is moving in the clockwise direction. Clockwise direction, right? Okay, so yeah, this is the thing to notice here. So I will observe this one, right? So of all this conclusion we'll get. So my like map contour will look something like this. Obviously I plotted this in Python. Okay, so like don't have to do this exactly, right? But what you can do, you just mark the threshold points, right? You just mark the threshold points. So here, right, I'm starting from here. This is the s equals to 1 point, right? If I just this is the s equals to 1 point, right? And what was at s equals to j? At s equals to j, it was 1 minus j. So I'm going in the clockwise direction, not in the anti-clockwise. So that's why the direction of arrow is like this. So if I go in the clockwise direction, right? So this is 1 and this is also 1. So this is the s equals to j point, right? S equals to j point. Okay, and what about this? This is basically the 0 point, right? So my mapped contour is touching the origin, right, at s equals to what? Minus 1. So this is the point at s equals to minus 1. So only these points you can validate. Okay, obviously when you draw it in rough, right, so you don't have to draw this exact curve. You can draw it something like this. Okay, that is just good enough. But the critical points you need to that should pass through the your rough contour, right? That should pass through the rough contour. So this is equal to s equals to minus 1 basically. Okay, so at s equals to minus 1. Now here, right, at this point again, if I put s equals to minus j, I'll get 1 minus j, right? Sorry, 1 plus j. So this is 1 plus j, right? 1 plus j. So yeah, this is this one, right? So like this is this plot. Now I again solve, like the thing notice here, this is clockwise and this is touching the origin. So yeah, those are the things that you need to observe. So again I will go into the next question. So next question has function like this, and the contour again, right, is the same contour. Okay, so obviously with the same contour we can make a valid comparison, right? So the contour is like this. Now this is at s equals to 1, right? And again, right, if you put s equals to 1, you get 0.33. Okay, here now my pole is at minus 2, not my 0 is at 0. Okay, just keep that in mind. Now if I put s equals to j, what do I get? I get 0.2 plus j 0.4, right? So that is what I get. Again, if you put s equals to minus 1, you get minus 1. This time you get a finite number, not non-zero number, right? And s equals to minus j, again, right, you get symmetrical. And what do you notice here? What do you notice? You notice that it is again moving in the anti-clockwise direction, right? Anti-clockwise. So I'm like my contour is moving in the anti-clockwise, and the mapped contour is also moving in the anti-clockwise, because this is positive, right? Imaginary component is positive. So anti-clockwise. Okay, this is moving in the anti-clockwise direction. So yeah, this is this one. Now like again, if you put s equals to minus a, you get minus. So yeah, it is absolute over here, and this, what you can see, is again symmetrical, right? Symmetrical around the real axis. Okay, so this is the plot basically. And what are the crucial points? Like here, right, this is starting at s equals to 1, then again like at s equals to what do you say, is equals to j, right? What was the point? It was 0.2 plus 0.4, so it will be somewhere around here, right? Somewhere around here, and then again it goes like it is going in the anti-clockwise direction. Then again it all of the way goes to which point? -1, right? -1. So it goes to -1. Real component is -1, right? And imaginary component is 0. That's why it touches here. Then again it is symmetrical around this, right? Real axis. Again it comes back here. Here again this is the critical point. Again this is 0.2 minus j 0.4, right? So yeah, again like this completes the whole contour, right? So yeah, this is the contour basically. Now what are the things to notice here is, so I wanted to notice that things to know, right? Things to like observation, or you can say, or things to notice. Okay, things to notice. So things to notice is basically can you notice, like I will obviously complete this in the next lecture, so this is just you figure it by yourself. I will tell this in the next lecture obviously. So can you notice when is my like this contour, like map contour, is rotating in the same direction in which my original contour was, like what are the conditions, and when does my contour like contain the origin, right? Mapped contour contain the origin. What are the conditions, like where is the location of poles and zeros, and how, is my poles and zeros of the mapped function, is it touching the contour, right? So can you make some criteria for that? Can you make some rules for that, right? Can you observe few things? Okay, so that is what I want to do. In the next lecture I will obviously may like tell you what are the observations, and in which case this like the direction changes, and which case it doesn't change, right? And in which case obviously my mapped contour will contain my origin, and in which case it won't contain my origin. So it all depends on the poles and zeros of my mapped function and the original contour, right? Whether it is touching or not. So that is the hint that I gave. So in the next lecture we'll obviously do the observations and do principal arguments, and also learn the criterion of Nyquist, right? What is the criterion of Nyquist stability? We'll try to understand that, okay? So yeah, thank you for watching this lecture, and I will see you in the next lecture.